All right, so I'm going to walk you through, well, several of the quantitative energy problems from worksheet 4. I'll do a couple at a time on each video. But here, remember, they're all basically the same thing. The key to these is finding out where you are on the heating and cooling curve. Okay, so we have a situation here. How much energy must be absorbed by a 150 gram sample of ice, so we know the mass, at 0 degrees Celsius, so we know the initial temperature, that melts and then warms to 25 degrees Celsius. So we need to find ourselves on this heating and cooling curve right here. Remember that the curve has 5 different sections. The solid is down here between A and B. And so you can warm up a solid, melt it between B and C. And then between C and D, you can heat the liquid, boil it between D and E, and then heat the gas. So we have a solid, a liquid, and a gas phase for any material. Okay, so there's 5 sections. The solid, either you're melting or freezing it, whether you're absorbing or releasing energy. You can heat or cool the liquid, you can boil or condense, and then you can heat or cool a gas. Remember that our y-axis is temperature, and our x-axis is time or energy put into it, and it is 2 directions. If we're going to the right, we're adding energy. If we're going to the left, we're releasing energy and cooling it. We just need to find ourselves on the curve. Okay, in this situation, how much energy must be absorbed by a 150 gram sample of ice? So it's ice. It doesn't say it's in any way melted, so it's ice, it's solid, at 0. And we know for water, this plateau, this freezing melting point is 0, and this boiling condensing plateau is 100 degrees Celsius. Okay, so if we're going to be at 0, that's right there, and it's a solid, so it's going to be right there at B. That's our starting point. It says it melts and then warms to 25 degrees Celsius. So we're going to start there. We're going to melt it, completely melt it, and it's going to end up at 25 degrees. So this is 0, this is 100, right about there is 25. So we've gotten ourselves on the curve right there. We know where we are. And we are in 2 sections. There was a section here where we are melting the solid ice, and then there's a section where we're heating the now liquid water. So that's 2 equations. And remember, we really only have 1 equation. We just have different constants. So it's Q is equal to the mass times the constant, the solid, heat of fusion, liquid, heat of vaporization, or gas, and a temperature change in these 3 sections where there is a temperature change. So in this first section right here, that's the Q is equal to M heat of fusion. So we're going to solve the equation 1 time for this section where we are melting it, heat of fusion. Then we're going to solve the equation again with the other constant, and it's going to be mass, and we're here in the liquid section. So Q is mass times C liquid delta T. Okay. So we just have to solve it twice, and you're looking for the total. So when we get the total energy, Q, from each equation, we'll just add them up to get the total for the entire thing. So it's 150 grams times the heat of fusion, which is 334 joules per gram. Okay. So you get out your calculator. 150 times 334. It's 50,100 joules. And so that's how many joules it takes to melt the ice. And then to heat it up from 0 to 25 degrees, it's the 150 grams times CL, 4.18, and then also times the change in temperature, and it goes from 0 to 25, so it's a 25 degree Celsius temperature increase. So 150 times 4.18 times 25. 15,675. So all you have to do is add them up. So it's 65,775 joules of energy to take that 150 grams of ice, melt it, and then heat it to 25. I also have an LOL chart here, and that's just your initial and final conditions. Okay? We have ice, that's our system. There's no chemical change, it's just water being changed from solid to liquid. It's still water. The phase change, well, it starts, it says ice, solid, and we know that ice gets 1 bar of phase energy, and in the end it's a liquid, and we know that liquids get 2 bars of phase energy. So it starts with 1 bar of phase, ends up with 2. Thermal, I like to think of 1 bar as 0 degrees, so I'll give it 1 bar because it started at 0. And then it ends up around room temperature, 25 degrees, so I'll give it 2 bars of thermal in the end. So it started as a 0 degree solid and ended up as a 25 degree liquid. Okay. I started with 2 bars, I ended with 4, so I had to gain 2 bars of energy into the system. Okay. And I hope you'll notice as we go through these that they're all basically the same problem. It's really just one equation. You can change the constant based on where you are on the curve, and you do as many of the equations as you are in those sections. Here we're in 2 sections, so we solved it twice. Okay. Let's try number 2 here, and this says, or this is number 3. Sorry, I want to do number 3. This is a 12-ounce can of soft drink. 340 grams at 25 degrees Celsius is placed in a freezer where the temperature is -12. How much energy must be removed from the soft drink for it to reach this temperature? All right. So again, we want to find ourselves on the heating and cooling curve. Remember, it's temperature and time, and then this is 2-headed arrow. If we're heating it, we're going to the right. If we're cooling it, like in this case, we're going to the left. This says we start with, we can assume it's water because it's soft drink, so it's about 95% water. And it says it starts at 25. So remember, for water, this is 0, and the melting is 100. So this is the 0 point, so 25 is up here somewhere. That's our starting point. And it says that it cools in the freezer down to -12. So it's going to cool the liquid, start to freeze it. At B, it will all be frozen, and then it will go even lower down to -12 degrees Celsius. So in this case, we are in 3 different sections. That means we're going to have to solve the equation 3 times, and that's okay. We'll take this first section here, that's the liquid section. Remember, solid, liquid, and we are also in here the phase change, the heat of fusion. So we'll solve that first section we started with, and that's Q is mass times the specific heat of liquid in this little section here times delta T. So all we have to do is plug in the numbers. The mass is 340 grams. The heat capacity of the liquid is 4.18 joules per gram degrees Celsius, and the change in temperature goes from 25 down to 0 in this section. Right? Starts here at 25, ends at 0, so that's a 25 degree Celsius temperature change. And if you look, you notice the grams numerator and denominator will cancel, the degrees Celsius numerator and denominator will cancel, and we'll be left with an answer in joules. Those are the only units left. So we take our calculator, and we say 340 grams times 4.18 joules per gram degrees Celsius times 25 degrees Celsius. And we get 35,530. So 35,530 joules. That's just to cool the liquid from 25 down to 0. Now we're going to solve how much it takes to actually freeze it all to a solid. And in that section, there's no delta T, but its Q is mass, heat of fusion. Okay, so mass is still 340 grams. And the heat of fusion, if you look on the top of the page, is 334 joules per gram. So 340 times 334. So 113,560 joules. The grams cancel. Okay. So it took 35,530 to cool the water. It released 113,560 joules to freeze it. And now we'll see how much it takes to cool the solid. And same equation. Q is mass, but it's the heat capacity of the solid times delta T. So it's still 340 grams, that's the mass. And the heat capacity of the solid, if you look up on the top of the page, is 2.1 joules per gram degree Celsius. And then the temperature change in this section, the solid section that we're solving for, it goes from 0 to negative 12. So that is a 12 degrees Celsius temperature change. So grams cancel, degrees Celsius cancel, and you'll be left with an answer in joules. So that's 340 times 2.1 times 12. 8,568 joules. So it took this much to cool the liquid, this much released to turn it into a solid, and then this much to cool the solid. In order to get the total amount, all we have to do is add these three values up. So 8568 plus 113,560 plus 35,530 is a total of 157,658 joules. Or if you were asked to convert it, we would multiply that it's 1,000 joules per 1 kilojoule. Joules would cancel, and we end up with 157,000.7 kilojoules of energy released.